Good morning, students. As we have discussed in our earlier lecture about the gravitational force, we are going to see next part of a chapter that is Kepler's law. As we know, there are the different planetary motions. As we discussed in our earlier video, the planets are revolve around the sun, moon is revolving around the earth. So how these planetary motions are working, how these things are happening, do they follow certain laws? So this depending on whatever the information is collected earlier by a scientist Galileo, using that all observation and other concept in the 16th century, scientist Johannes Kepler studied that all data made available by before scientists, and he found that there are certain laws are followed in these planetary motions, and he explained that laws in three parts, and that is what we say as the three laws of Kepler's, which are also called as laws of planetary motion. So we are going to see the first law here. So first law given by the Kepler says that the orbit of planet is an ellipse with the sun at one of the foci. What the Kepler says, when as we say the planets are revolving around the sun, and as we have already discussed, the solar system, it's not exactly a circular, it is little bit oval shape like egg shape, and that shape is nothing but it's called as a ellipse. How that ellipse is formed, you can read in the textbook, that whenever the cone in mathematics, whatever the cone we are having, when that cone is cutted in an inclined plane, whatever the surface you are going to have, that is what called as a ellipse. You can see the diagram in the textbook, page number 3, diagram 1.3, how it is. So that is not very important. With the important part, that is the law, first law of the Kepler, that law says the orbit of planet is an ellipse with the sun at one of the foci. Means whenever the planets are revolving around the planet in their orbit, so that orbit is in the form of a ellipse, and where the sun will be. So when we talk about the ellipse are going to have a two focus, and therefore it is called as foci. Okay, and it is going to have a two focus, and therefore the sun will be either at a one foci. Which foci that we don't know exactly, it will be at a one of the foci. We can consider any one side of the focus. Okay, so just see the diagram. This is what our diagram we are having. This is the circle which you can see, that is our focus. Okay, so this part, this is the sun. So this is one focus here, and this is the another focus you can have for the ellipse here. So sun is at a one of the foci. Now suppose the planet is going to be here, so the planet will start revolving. Okay, it will start revolving in this way, and it completes a one ellipse, and that is what the first law says, the planets revolve around the sun in a ellipse. So the orbit of planet is nothing but a ellipse shape. That is what you have to just remember. We are going to have a next law now, that is a Kepler's second law, and Kepler's second law says sorry, the line joining the planet and the sun sweeps means covers equal areas in equal intervals of time. Understand this part properly. The line joining the planet and the sun, now this is your planet. Okay, this is your planet here, and this is the sun. So when this planet and sun are going to join, so this line when you're going to draw, so this line sweeps equal areas. Sweeps means covers equal areas. Okay, now suppose this planet is at a position A. Okay, now when it will start revolving, so planet is going to revolve around the sun, means from here you are going to connect the planet. Now when it will start moving, it will be revolve. Correct, it will be start moving from here, this direction, and it will reach the position say B. 1 minute. It will reach the position B here. Okay, now the line is, when the planet is here, the line joining is this, we can say this as a O. So OA. correct? In a book you are given S, so we'll take S only better. Sun, so we'll take as a S. So when the planet is at A, you will be having the line SA. When the planet is at B, you will have a line SB. Okay. So when planet moves from A to B, this position, it is going to have this much area as SAB. Are you clear, able to getting what I'm saying? Okay. So this area, and suppose if you consider the planet at this position, here suppose the planet is now, another example we will consider C. At position C, the planet starts rotating from here and reaches the position D. Okay, this position. So when I will join these 2 points from here, so when it covers the area is nothing but SCD. Okay, so now we are considering two position. When the planet is at A and reaches the B, so it covers how much is area SAB. When the planet is at C and reaches the D, the area cover is a SCD. Okay, now you can see the area, you can look different. The length, if you are going to see, it's different. But when you calculate do the calculation by considering the proper formula, the area which you are going to get, that is what equal areas means. Area SAB and area SCD are going to be equal, and that is what the law says. When the line joining the planet and the sun sweeps equal areas in equal interval of time. Now when the planet from A to B, it reaches to reach B, from A to B, suppose it takes a 1 minute. So in that 1 minute, suppose we say the area cover is say 2 centimeters square. Okay, something 2 centimeters square. Now when the object is planet is at C and reaches D again in 1 minute, so the area cover is going to be again same as a 2 centimeter. Is it clear? Means the area cover from planet A to B in 1 minute and the area covered from planet C to D is going to be same. That is what says the second law. See, read here. As you can see in figure, when planet is at A, reaches at B in time T, covers area ASB, as I told you. Similarly, when planet is at C and reaches the D in time T, covers area CSD. Okay, so by Kepler's law, area of ASB is equals to area of the CSD. So that is what I explained you. When the line joining the planet S to A, that is SA, when it reaches to B, so the area cover is nothing but SAB. Okay, this area is going to be covered in time T. Now when the planet is at C and reaches the D, the area cover is nothing but CSD, means this much area is there. And according to the Kepler's second law, these both areas are similar. Means suppose this first area is say 2 centimeter square centimeter, this is also 2 square centimeter. Suppose this is a 25 square centimeter, and this is also 25 square centimeter. Hope you have understood the law. Let's move to the third law, that is the Kepler's third law. The square of planets period of revolution around the sun is directly proportional to the cube of the mean distance of planet from the sun. See, read again what it is says. The square of planet's period of revolution. Now you know what is a period of revolution. The time taken by a planet to complete one round around the sun, that is what called as a period of revolution. So suppose that period of revolution of planet say T. Okay, so square of that T, square of planet period of revolution means square of T is directly proportional. It is going to be directly proportional to the cube of the mean distance of planet from the sun. Means from planet to the sun, what is the mean distance? So say as a S to A. So that is what your mean distance. We'll assume that as a R. So that T square is proportional to the R cube. Means period of revolution will be increasing with increasing in the length of the mean distance. Is it clear? That is what I explained. Suppose R is the average distance of the planet from the sun. Means from S to A, the distance is a R. And T is the period of revolution. Means from A to complete the one round and come back to the A, the planet takes a period of revolution, say capital T. Then by Kepler's law, T square is proportional to R cube. Means if your mean distance of the planet is increasing, time of revolution will be increasing. Mean distance is decreasing, so time of period is also decreasing. So that is what we know already, as we are studied in 7 8 standard. The a series of our planets. Now first we are having the Mercury, then Jupiter, then Earth. That what series? So the Mercury is going to take very less time, within just one day, 24 hours something. It covers one, completes the one round. But that only for the other planets which are very far, the Jupiter or the Saturn, all that, they will be taking the years to complete one round. Mercury is going to complete in 1 or 2 days, but that is only Saturn and others are going to complete even within a 1 year one round, because they are very far. Means the mean distance is very high, and therefore the time period revolution is also increasing. So you have to remember that square of planet's period of revolution around the sun is directly proportional to the cube of the mean distance. Means mean distance is increased, period of revolution is increased. Mean distance of the planet is decreased, the mean period of revolution is also decreased. So t square proportional to r cube, so t square is equals to k r cube. K is nothing but constant we are using, so t square upon r cube is equals to k. Means the ratio of the period of revolution to the mean cube of the mean distance is always a constant. And these three laws of the Kepler's are given by the position study of position of planets by regular observation. He made a regular observation of the planets position, he studied about them, and then he gave us these three laws which are very important. You have to study all the three laws, and remember it can be asked separately one, it can be asked in a fill ups true or false like questions, or you may get a 3 to 4 marks question also explains planetary laws of Kepler's with the help of a diagram. So this whole thing you are going to write. Okay. Let's the next part. That is what our Newton's law of gravity, universal law of gravitation. Now we have discussed in the first video started, that is about a gravitation, and we have discussed that gravitation is nothing but the force of attraction between the two objects in the universe. So that is what explained with the help of a law properly by the Newtons, and that law is called as a Newton's universal law of gravitation. Let's see what he says. So every object in the universe attracts every other object with a definite force. As we have started with the first video, in that we have said what is the gravitation. It's nothing but the force of attraction between the two objects in universe. So same thing is repeated here. Every object in the universe, every object, no, it's not a concept of big or small or the anything. Any two object you can take in the universe, they are going to have the attractive force between that. So they will have a definite force. This force is directly proportional to the, that force is going to be directly proportional to the product of the masses of the two objects. Whatever the two objects you are going to take, whatever their masses, their product, and is inversely proportional to the square of the distance between them, and inversely proportional to the square of the distance between them. So now you know directly and inversely. Directly means if one quantity increases, other is also going to be increased, and inversely means if one quantity decreases, the other quantity increases. Now as we say, the directly proportional to the product of masses means what? If you are going to take two objects of particular masses, the forces depend between the these two masses. If that masses are increased, the force is also increase. If that masses are decreased, the forces is going to decrease. And the for two objects are going to be have attractive force, means it comes in the non-contact force, means they will be not directly in contact with each other. There is some distance between that two objects. If that distance is going to be less, the force will be more, and if that distance is more, the force is going to be less, because it is a inversely proportional. Okay, so that is what a Newton's law explains. The force of attraction, every object in the universe attracts every other object with a definite force, and that force is directly proportional to the product of masses of two objects and is inversely proportional to the square of the distance between them. Let's see with the diagram. So this is what we are going to consider mass m1. This is a mass m2. They both are in the universe. So you can see these arrows. These arrows are nothing but the attractive force between them. This m1 is going to be attracted by m2. M2 is going to be attracted by m1, as the law says. They are going to have a very attractive force between each other. then this d is nothing but the distance between them. They can be very close, they can be farther, so that d is the distance between them. Okay, so as shown in the figure, two objects with masses m1 and m2 kept at a distance d from each other. Mathematically, the gravitational force of attraction between these two bodies can be written as. So now whatever this law we have discussed, so how it is mathematically represented. So as the first line says here, this force is directly proportional to the product of masses. So F is, this symbol is called as a proportionality symbol F1 into M2. Product means M1 multiplied by M2. Okay, so F is directly proportional to M1 into M2, and F is inversely proportional to 1 upon D square. D is nothing but the distance between the two objects. I hope you are clear. And by combining together, you can say F is proportional to M1 M2 upon D square. Means F is directly proportional to the product of masses and inversely proportional to the square of the distance between them. Okay, this is a concept. And two, by removing this proportionality sign, we can get a constant F is equals to G m1 m2 upon d square, where G is nothing but a constant of proportionality. What the G is called? Constant of proportionality. How in earlier example Kepler's we have used a K, so that is we have used a K. Here we are going to use a capital G, and this capital G is called as a constant of proportionality. Okay. Hmm. Now further you are going to have G is the constant of proportionality, also called as a universal gravitational constant. So G is also called as a universal gravitational constant. Why? The law is all over. For universally this law is applicable, and therefore this gravitational constant is called as a universal gravitational constant. Now for the gravitational constant you are going to derive a derivation. So from above equation means this equation. From this equation now you are going to derive the further part, so that G is equals to f d square m1 m2. See here what we are having, F is equals to G m1 m2 upon d square. Now when you want to find the value of G from this equation, above equation, correct, this equation, what you will do, this d square which is divided when it comes here multiplied, so therefore it becomes f d square. M1 M2 is in the numerator, means it is multiplied, so when it comes on other side it becomes divided. So G is equals to FD square upon M1 M2. I hope you understood. So you will be getting G is equals to, now F we will keep as it is, D square you are going to take 1 centimeter. Means suppose the distance between this M1 and M2, these two objects is how much? 1 centimeter, and the masses of both the objects are 1 kg 1 kg. Okay, both the masses are of 1 kg and the distance between them is a 1 centimeter. Then we say G is equals to F. Okay, then G is equals to F means what? So my gravitational constant is nothing but the force between the two objects of a unit mass which are at a unit distance. That is what the definition of our gravitational constant, which I think you have studied in the ninth standard. I not remember exactly, but you have studied, I think. So, thus, universal gravitational constant is defined as the gravitational force between two objects of masses 1 kg kept at 1 meter apart. Okay, here my mistake is just not centimeter, it's a meter, 1 meter. So make changes here. Remember, this is not a centimeter, this is a meter. Because we are considering the SI unit. So SI unit of a distance is a meter, not centimeter. So my mistake. So when we are going to consider the two object of a unit masses means 1 kg, and when they are kept at a 1 meter away from each other, whatever the gravitational force they will have between them, that force is called as a universal gravitational constant. I hope you people are cleared. Read it properly, and if you have any doubt, we'll discuss in our live lectures. And the SI unit of G is a Newton meter square per kg square. Now how this G SI unit is derived? So again we'll come to this part here. What is our F unit? F is a force. What is the unit of force? So that is a Newton. D is what? Distance. So distance is measured in a meter. So it's a D square. Therefore it is a meter square. and mass into mass is measured in kg, so kg into kg, so it will be kg square, but masses are in the denominator, therefore per kg square. Is it clear? So remember that unit. It may be asked again MCQ like questions or a true or false. So the SI unit of a G is a Newton meter square per kg square, and its value is found. If you are going to solve this formula, these values properly, by taking the proper distance and the masses, you will be getting the value. This is a constant value is taken, you have to remember this value. That value of a G is a 6.673 into 10 raised to minus 11 Newton meter square per kg square. Okay, so you have to remember this value also. Now you can see here line is given and here minus 2 is given, here just 2. Why this 2 is given? Because it is given line, means that line shows per, and here to remove that per we are going to take as a minus 2, because when it comes up the index become minus. That is mathematically you have studied. So just remember the SI unit of G is a Newton meter square per kg square, and its value is a 6.673 into 10 raised to minus 11 Newton meter square per kg square. I hope you understood all the three laws of Kepler's and Newton's universal law. If you are not getting, just listen it once again and read the laws from the book. Otherwise after that also, if you will have any doubt, we'll discuss that in the live lectures when we'll start, or you can contact me through the comments. The next part we are going to have now, as we said, the force of attraction is depending on the distance between them. So that distance, how you are going to measure the distance? Because when you are going to consider any two objects, they will be not of a same size or the same shape. There will be different types of shape, we know. So how we are going to measure that distance? And therefore we are going to have the next part. So shape of the body, direction of force, and distance between bodies. Now when the body is going to be properly spherical, then the direction of force is going to be line joining the centers, as we discussed in our earlier slide. As you can see, the both are circles, so you have seen the line which is to from the center. Correct, it is exactly in the middle. It is not shown at a particular side of the circle, it is exactly at a middle, means force is acting towards the line joining the centers. And distance between the bodies is going to be distance between their centers. You are going to measure the distance between their centers. So again, you have seen in the earlier slide the line which is shown down, but it is shown from the center only, means whenever the body is spherical, you are going to consider the distance between their centers and the line joining the centers. But when the body is irregular, where is the direction of force? So it is along the line joining their centers of masses. Okay, the force will be acting towards a line joining the center of masses, and distance between their center of masses, the distance is also you are going to take as a center of masses. Now what is this distance and what is that center of mass? So center of mass is nothing but it is defined as, it is the point inside or outside. Okay, the point will be inside the body or outside the body, outside the object, at which the total mass of the object can be assumed to be concentrated. Okay, so it will be a some point which can be inside the body or outside the body depending on the shape of the body. At that point the whole mass of the object will be concentrated, and that is what we say as a center of mass. So now when the shape of object is a spherical, you can see its center of mass is at its geometrical center, means if it's like a circle, if you are going to consider, so its center of mass will be at the center. And that only if you are going to consider any other object, means if it's any irregular shape, then its center of mass will be at its centroid. Centroid means you are going to draw medians, and the middle point which you will be getting, that is a centroid, that you will be cleared mostly in the mathematics part. Okay, and this centroid, this center, geometrical center, means it will be exactly lying inside the object only. But when you talk about this centroid point, now that as the definition said, it is a point inside or outside. So when you talk about other object, means any irregular shape, so depending on the shape, that center of mass can be inside the body or outside the body also. Okay, so here we have finished with the next part of the chapter. So in this we have covered three Kepler's law and the Newton's universal law of gravitation. So just listen the video properly. If you are not getting, listen it properly once again, read the textbook and clear your doubts. If you have any, after that also, if you have any doubt, you can contact me. And